Welcome to my presentation, which is entitled New Microwave Sensing System for Blade Tip Clearance Measurement in Gas Turbines. In my presentations, I will give you first the context of not the thesis, but the work, of course, which is health monitoring techniques for rotating machinery. Then I will talk briefly about the state-of-the-art existing solution and propose a new one, on the basis of which I will draw some conclusions and give you some perspectives. Okay, the context of my work dealt with health monitoring techniques for rotating machinery. This technique is very useful for the health monitoring of turbine engines and turbine rotating machinery in general, and is essential specifically for the engine efficiency and safety. And it enables also some specific kind of system which are real-time blade tip measurement systems, for which the microwave probes prove to be a very reliable technology among the others. Okay, to go a little bit more in detail, I would say that the system that we investigated, it's a system that whose principle of operation is similar to a short-range radar. In my presentation, we will deal with this part of the system, which is the front end, the microwave front end of the system, which is a microwave sensor that sends and receives the microwave towards the passing blades, which are to be considered the target of the short-range radar system. And of course, we have a signal processing unit, which is connected to the microwave sensor by means of a high-temperature coaxial cable, and then the signal displays is directly usable by engineers. Okay, the system performs tip measurement. Specifically, two kind of measurements are possible with this kind of system, meaning the clearance, which is the distance between the microwave sensor and the passing turbine blade, which is essential for the engine safety and continuous monitoring of the engine, and the time of arrival, which enable also the monitoring of unwanted vibration that an engine might have. So here you see the antenna that sends the microwave signal, which is modulated by the target and comes back. So for this specific application, the probes that we envisage to propose should be, of course, compact, not to interfere with the operation of the engine. And of course, it's very desirable that are simple and robust to allow reliable measurement for elongated, for long periods of time. And as candidate for industrialization, of course, these probes are better to be simple to allow better repeatability. Of course, microwave technology, as I said, is really suitable technology for this application because it's inherently able to operate in the presence of dust particles and all the agents that might be present in a turbine engine, including really high temperature range that might go from -30 degrees to up to 1,000 degrees, depending on the turbine stage. As a state-of-the-art, I would briefly list the existing other techniques that can be encountered in literature that are capacitive, eddy current, optical, and microwave sensors, of course. The first two, I would say very briefly, that are, of course, inherently very sensitive to high temperature variation. The third one is probably the most the best one for what regards sensitivity, spatial resolution. Sorry, but of course it has problems due to the presence of dirt and dust inside the turbine case that might disable the operation of this kind of sensors. What we are proposing is new solution based on microwaves. So at the beginning of this project, one existing solution that was also investigated in my work was a patch antenna probe, so an antenna-based kind of microwave front end, which is operating at 5.8 gigahertz and was patented by the Shamer and others. So we investigated this sensor that was characterized and studied in order to find to possibly propose new solutions. What we remarked after investigation is that the patch is unreliable and strongly affected by temperature. In fact, we found how some prototypes were affected by spurious resonances, and anyway, this kind of probe was not able to operate for long periods of time if there was no cooling system present. In order to provide acceptable measurement in possibly smaller turbines, we need, of course, smaller devices, and a solution is working at higher frequency, for which we chose in particular to 24 gigahertz. And for this purpose, of course, simple structure are needed to enable both mechanical robustness and repeatability of manufacturing process. And one another feature that is highly desirable is some probes that are good for close perturbation with a near field kind of interaction. In fact, the patch antenna probe was found to have a very, I would say, complex kind of interaction with the blade, which was in the very near field of the antenna probe. For this reason, we want to move to another kind of technology to enable a more simple to use and simple to study kind of interaction. The requirements that we had for the new microwave probes were that they had to have a single resonance in a 5% band, linear phase, and stable performance versus both vibration and the presence of abrupt high temperature variations. In this kind of application, of course, the use of high temperature material is a must, and then we have to still respect the compact size. For us, the targeted diameters were less than 12 millimeters, but we achieved better. And most important, a weak sensitivity to the mounting orientation of the probe, because due to vibrations, both the axial position, which is the position of the probe with respect to the leading edge of the turbine blade, and the mounting orientation of the probe might change. So we need a probe that is weakly sensitive to these kind of changes. What we propose is a very, very simple principle of probe, because the resonator-based probe that you see here, it's basically a metal cavity which is fed by a coaxial cable, which launch the wave inside the cavity by means of either a pin or a loop. All the four configurations here are possible and give analog results. But this first configuration was chosen for optimization just because it was more practical for the customer that required it. So this kind of probe was found to represent a valid alternative to the more complex antenna-based resonator, and was intended for blade tip measurement in small size turbines, like the ones that you might find in aero-derivatives or aero-engines. As a sample result, I would just give you what the blade probe interaction looks like. Sorry, I had to hide this, so no nice picture due to confidentiality, but this enables you to see how the blade probe interaction is, so very neat and clean with respect to the patch antenna probes kind of interaction that leads to spurious resonances in this area. So what regards the measurement of prototypes, we have here a comparison between the measured and the simulated results, showing excellent agreement, and the repeatability of the built prototypes was acceptable for the specific applications. For what regards the tests that were run on the prototypes, among the environmental tests, so those tests that were done in lab with dedicated test beds, we have vibration tests in 2 different bands, thermal tests that included isothermal aging at 900 degrees for over 3,500 hours, and thermal cycling from room temperature to 850 degrees with 5 bar cooling air for about 1,200 cycles. And then finally, I will show you sample results about the installation sensitivity test. Basically, the probe orientation was changed so that the optimum position found here in the blue spot, we have very good linearity between what is the measured clearance and the real one. So finally the on-engine tests, which are the tests that were run in a true engine at the customer, were of 2 kinds. The first one is aimed to show how the system is capable to detect the clearance variation through the engine operation modes. This is shown in the first figure. You see that when the engine, this is the red line is the rotation per minute of the engine rotor. When the engine is shut down and endures a cooling period and then a hot restart, the clearance that they are detected by the 8 channels, each of them corresponds to a probe. Well, all of the channels were detecting the change of clearance accordingly. And then the second result is the capability to detect the single clearances. For these specific kind of measurements, some of the blades were shortened in recognizable patterns, and you see that the 8 probes are capable of detecting them. Of course, you see here that there are small discrepancies between the probe response that might be due to the different sensitivity of the probe to the blade geometry and to the calibration. So the work done in the frame of this application allowed us to reach some conclusion that might be listed as follows. Okay, we investigated some existing solution that was based on an antenna probe, which frequency is set by the antenna geometry, which is relatively complex and has a large propagating field, while the near field distribution is maybe not appropriate for small range sensing. As I said, the structure is complex, so these kind of antenna-based probes might be suitable for larger clearances. On the other hand, the resonator-based probes have a relatively simple structure that allows to tune the frequency by appropriately choosing the length of. Okay. So this simple structure might allow more robustness and stability, and might be suitable for more small clearances. So, as for the conclusion, some microwave front ends were developed for the purpose of blade tip monitoring, and in specific, the resonator-based solution were proven to be suitable for the blade tip sensing, and are now protected by patent application, confirming their suitability for the considered aim of work. Thank you.
So the presentation is over.